So let's go ahead and write ourselves a toString method. And I'll make a better version of this in a bit. But it is fairly straightforward. Except for the fact that, of course, we will need a, this will just simply be a wrapper method. Return toString. This dot root. Okay, and let's go ahead and make our private method. Now, private method, private string toString node e root. That should take care of that. Straightforward. If root is null, if the subtree I'm at is null, then return empty string. Otherwise, let's do this. Let's just simply print out stuff in order. So we want to return, let's make a string output is equal to nothing. Although that's actually an inefficient way of doing it. Instead, I'm going to use something called a string builder. What a string builder does is that it is a way of basically concatenating a bunch of strings together. Using the plus operation to build strings is actually pretty expensive. So I think string joiner is a new version of it, but I know how to do it with string builder. So I'm going to use that. So builder.append, and basically whenever you want to add something to the strings you're concatenating, you just use builder.append. So here what we're going to do is that we are going to figure out what the left subtree is. So builder.append toString the left side. So we're going to append what's on the left side. Builder.append a space to separate it. Then we're going to builder.append this dot, or rather not this dot root, but root.data item. And then we'll do builder.append a space, and then builder.append converting the right node to an item. Root.right. Okay. And whoops. That was okay. Root. And now we return builder.toString to convert all what we just appended into a string. So let's try it out. PSVM. Let's go ahead and create this tree over here. Binary search tree of integer. BST is equal to new binary search tree. Okay, bst.add. The first thing we need to do is add 15. Bst. Let's add on the right side first. Add 50. Bst.add 20. We need to add the 50 before the 20 because otherwise the 20 would be on a higher level. So bst.add 10. bst.add 13. bst.add 12. bst.add 7. bst.add. I should have Control-C, Control-V'd. And then out bst. And 6, 7, 10, 12, 13, 15, 20, 50. But how do we know that the structure of this is maintained? Well, that's an excellent question. So what we're going to do in this case is a preorder traversal, and this is an algorithm that's going to come from the book. So as you can see, the toString just got modified to use our standard concatenation, which I mentioned was expensive. But this will use a string builder. So for a toString, we make ourselves a string builder. Then we do pre-order traversal, and then SB. And then, so we're going to use the string builder, and then we have the def thing. And it's easier to show you what this does, which is very interesting. So, okay. Let's go ahead. So it does bst.node. So why don't we go ahead and add a true string? So this is just, so it's trying to add our node. So let's go ahead and add a toString for our node itself. Public toString. And what this will do is instead we're going to return item.toString. That's easier. Okay. Now this looks a bit weird, but once we process through it, it'll make it easier to see what's going on here and then easier to see your code. So what's over here is the indentation levels. So this is the first level. This is the second level of the tree. The third indentation level is the third level of the tree. The fourth indentation level is this fourth level. So notice 15 is the root. Then we've got 10 and 50 on the second level. Then the third level has 7, 13, and 20 on it. And then we also have a bunch of nulls. This is just simply because we need to put something in those spaces when we print it out. So 15 is the root of the tree. And then on the next level, we have 10 and 50, which are 15's left child and right child. Then 10 has two children. It has 7 and 13. 7 is 10's left subchild. 13 is 10's right subchild. It's very hard to print out a tree in ASCII and do it in any kind of console-friendly format, but this is a decent way. 7 has two children. It has, or rather has 6 for its left child and null for its right child. 6 has no children, null and null. So that's why we get these nulls over here. So basically, each indentation has the left child followed by the right child of the indentation above it. And then 50 has left subchild 20 and null. How does this do this? It is using this pre-order traverse, which just simply says root, whatever def we're at, and the string builder. So this is a pre-order traversal, which means we handle the root, then the left subtree, then the right subtree. The first thing we do, remember, everything is made as a local decision here. We say, okay, I'm currently at this node. And I'm keeping track of what depth this node is. In other words, what level I'm at. So if my level is equal to 1, or whatever, depending on what my level is, I'm going to print out two spaces. So if root is equal to null, if we're an empty space, we're just going to add null here and a new line so that we can move on to the next line. Otherwise, if I'm not null, because it's pre-order traversal, this is the way it needs to be for pre-order traversal, I will handle myself first and put down a new line. Then I'm going to handle my left subtree, and then I'm going to increase the depth there and handle my right subtree. Let's take a look at actually what would happen if I do this as in order and see what kind of craziness this gets up to. Yeah, it does not look good at all. So instead, what happens if we do, oh, I don't know, this over here? Let's see. There's an issue of getting our... Is it an issue of putting everything into the right place, I wonder? That null? But notice that everything's coming out in order over there. It's just our indentations are all messed up. Well, regardless. That was just experimentation on my part. Don't want to waste too much time on it. But this gives you this structure, which is kind of useful.